right? And then after that, we are going to have a second stage pump, whereby this is from the feed water heater pressure, which is the blade pressure also, being pumped into the boiler pressure. So as for the TS diagram is concerned, then we could see that 1 to 6 is the first expansion, the first part of the expansion in the turbine. And then from 6, we are going to blend some of the steam in the turbine to be flow to the feed water heater. So this is what we have from point 6. This point 6 doesn't mean that it's going to be a saturated vapor. It could be superheated vapor and it could be mixture. Usually it's still superheated vapor. So we must take care of the state of 6. Okay. And then the rest, right? If we blend Y kg right here, the rest is the balance of this Y kg, which is 1 minus Y, will be expanded throughout the balance or the rest of the turbine component. Then coming out here is 2. This is coming out from the turbine exit is 2. And then it's being flowed to the condenser. Right? And then the same amount, 1 minus Y, we are going to pump in the first stage pumping process to stage 4, to state 4, and then mix with this Y kg. What is we have right here is 1 minus Y. Okay, 1 minus Y kg, the balance of the steam that been expand in the turbine. Okay, so as far as the mass conservation is concerned, we can see that 1 minus Y plus Y, what is coming out at state 7 is 1. Okay, is 1. And then the rest is 1, 1. From here is 1 kg, 1 kg, or the fraction of mass is 1 kg up to 0.6. Okay, so this is what we have as far as the regenerative is concerned, right? And we also could have a system, or we could have a cycle whereby we have the two-stage expansion with reheat. Okay, two-stage of expansion with reheat and incorporate with the feed water heater. In this case, there is no reheat. Okay, what is balance? The balance of the steam after bleeding process is being expanded throughout the balance component of the turbine. Okay, and if we look in terms of the work right here, the work output for the first stage of the expansion is W16. Let me have a copy of this and I transfer to the whiteboard. Okay. Print screen. Now we are going to analyze as far as the what happened to my internet? There's no hello. Okay, guys, can you hear me, guys?
Yes, sir, I can hear you.
It seems that like it said right here there's no internet connection. Okay, connected already. Okay. Okay, what I do, I just close this software, this whiteboard, and reopen it again.
Doctor, try checking your Wi-Fi connection again.
Yeah, this is my connection. No internet network. But I could contact you all, right?
Yeah, we could hear you. That's so weird.
Let me see that. What should I do? I read the any suggestion, guys? What can I do? Reconnect again or let me see. Wait, I try to reconnect again. Okay, that's it. I just log in again. Okay, this is our TS diagram. So now we are going to see the analysis of the energy balance. Okay, energy balance. Can you guys see right? My connection is still seems that.
Yes, Doctor, I can hear you.
Okay, right. Okay, thank you. Okay, the thing that we need to look at this is to have the energy analysis or using the SFEE for each component. Before that, I would like to remind you all, if this 1 kg is basically based on a flow of 1 kg per kilogram. Sorry, 1 kg of each flow, because we know that the enthalpy is kilojoule over kilogram. So it's taking care of every one fraction or the one portion of the steam flowing. I would rather omit this kg. I don't like to use this kg because it's some sort is misleading for us. Just assume that the flow fraction is 1, and then again the rest of it is 1 y and also 1 minus y, right? So as far as the work for the turbine, this is equal to the sigma work of the turbine. This is equal to the W12, W16 plus W62. Okay, and if we get the formula, the equation for W16, this should be H1 minus H6. And the fraction of flow right here is 1. Okay, this is 1. So what the unit of W16 is in kilojoule over kilogram. Right? And for the rest of the expansion process, which is 6 to 2, which is W62. This is equal to the H6 minus H2. But remember that we have bled the system at 6. So the rest or the balance of the fraction of flow is 1 minus y. And right here, we're still getting the unit of kilojoule over kilogram. That's why I don't like to put the kg right here. Because if you put the kg right here, as though that the work is in kilojoule, which is extensive. But in this case, we are getting the work as intensive properties regarding to the or subject to the unit of the enthalpy. So I would rather use a fraction without any unit. Okay, you see, this is the fraction without any unit. This is the fraction of flow without any unit. So that we could get the W16 and W64 is still in kilojoule over kilogram, which is the intensive or the specific enthalpy. based on the change of specific enthalpy. Okay, so this is as far as the W16 and also the W62, which is involving the expansion process of the turbine. And this is what we could have in as far as the work output or the gross work produced by this turbine. Okay. Now, if we look the rest of it, which is our interest is the Q in. Okay, Q in. The Q in right here, if we look to the schematic diagram, this is the schematic diagram. The Q in is from 8 to 1. Okay, the Q in is 8 to 1. If you look at the feed water heater, the energy obtained from this Y at state 6 is still from or originate from this boiler and also this superheater. So as far as the Q in is concerned, the Q in is only in this part, which is the boiler and the superheater. Okay, which is from 0.8 becoming 0.1. Right? It's not from 0.4. The 0.4 to 0.7, the 0.4 to the 0.7, the increment of energy in terms of enthalpy right here is because the incorporation or the integration of the feed water heater. So from 0.4 to 0.6 is the increment of enthalpy because of the feed water heater. Right? And as far as the Q in is concerned, starting from 8 to 1. That is the use of this feed water heater. The feed water heater, the purpose is to reduce the Q in or reduce the Q in order to increase the thermal efficiency by what? By increasing the average temperature at the boiler side. See, we increase the temperature at 0.8. Therefore, what we have right here is the getting an average of 8, 5, and 1, the temperature. That is the method used in order to get what we said as the increase in thermal efficiency of this plant. As though that we are trying to get as isothermal as possible of process 8, 5, and 1 as what we can see for Carnot cycle. Okay, so we are going to increase or to average it up for a small value. So that's why we can increase the thermal efficiency of this type of cycle. So as far as the Q in is concerned, this is equal to Q81, which is equal to H1 minus H8. And if we look the fraction of flow as 1 to 8, you see right here, this is 1. Okay, and then this is 1 minus Y. And then we can see that 1 minus Y flowing to 2, 3, 4, and 6 again. But what happened in 7? What happened in 7? We have mixed the 1 minus Y and Y. So what is coming out from the 7 is 1 fraction. So as far as the flow fraction is concerned right here, this is 1. Okay, this is 1. So this is the Q in. Right? And then for the condenser, which is Q23, this is equal to the fraction of Q23, the ejected heat at the condenser side. This is 1 minus Y, H2 minus H3. And then for the pumping work, W34, this is equal to 1 minus Y, H4 minus H3. Okay, and then the pumping work for W78, this is equal to the fraction of flow, combine it, this is 1, H8 minus H7. Right? So of course, to get the V time delta P, whereby this is the formula that we use to get the W34. So this is equal to 1 minus Y V P4 minus P3. And for W78, this is equal to 1 multiplied by specific volume, which is 0.001. This is P8 minus P7. Okay? So this is the analysis for each component of the cycle, the regenerative cycle. So after that, if you want to get what is your W net, your W net is equal to your sigma W for the turbine minus the sigma W for the feed water pump. Okay, we have 2 right here, which is W16. This is W62. And right here also, we have 2 components of the W feed water heater, which is W34 and also W78. Okay? Right. And then if the flow of this 1 kg is m dot, let's say we have m dot right here. Let's say the flow in right here is m dot. So if this flow is m dot, meaning that m dot times 1, the flow rate is m dot. While for the flow of Y, which is the blast stream, this is m dot multiplied by Y. This is what being flow at 6 to 7. And then for the condenser, we just multiply m dot. So this is the amount of flow at the condenser side. So the m dot for the boiler is 1. Okay, which is multiplied by m dot. And then the m dot for the blast steam is equal to Y multiplied by m dot. And for the m dot for the condenser is equal to 1 minus Y multiplied by the m dot. Okay, so this is the flow involved. And again, for the feed water heater right here, the flow at the feed water heater 3 to 4 is m dot multiplied by 1 minus Y. And the flow rate of the second feed water pump 7 to 8 is equal to m dot times Y. Sorry, is equal to m dot. Okay, because we have mix right here. So what is coming out from 7 and also 8 is m dot. Okay, so as far as how to determine the mass flow rate, this is what we do. And if we put the mass flow rate in our equation, let's say we put the m dot right here. So this becoming W dot. And this we will get in kilowatt. Again, for the W62, If you put here m dot, then this becoming w dot, and this will become in kilowatt. Same goes for the Q in. This is w dot, this is m dot. So the unit of this Q in is in kilowatt. Same goes to the Q23, the condenser side. It's multiplied by m dot. So we are having right here in kilowatt. Same goes for the rest. Okay, same goes for the rest. For the feed water pump, just multiply by m dot. Then we get here w dot in kilowatt. This is m dot. It is in kilowatt. This is m dot. This is in kilowatt. So this is how you get in terms of kilowatt, the rate of heat and also work involved in this type of cycle. Okay. So if you look carefully, in order to get what is W net and Q in, which will determine our thermal efficiency, then we need to get all the enthalpy. Okay, we need to get all the enthalpies involved in this type of case. So how to get H1? Cost, usually H1 will be determined by P1 and T1. Okay, let us recap how to get the enthalpy for each case. All right. So to get what is the H1, we are going to use P1 and T1. How to get the H6, we are going to use P6, and S6 is equal to S1. How to get the enthalpy of H2, we are going to use P2, condenser pressure, and S2, which is equal to S6, which is equal to S1. How to get the H3? H3 is the HF at P3. How to get the H4? H4 is equal to H3 plus W34. How to get H7? H7, right, is at equal to HF at P7, which is at the pressure of bled steam. Okay, and how to get the H8? H8 is equal to H7 plus W78. Right. In this case, if we are getting the enthalpy, when we determine the enthalpy, please don't take care of the fraction, assuming everything in is one. The flow is S1, the fraction is 1. Okay, you see that here? H4 is equal to H3 plus W34, where W34 is equal to V P4 minus P3. When you are determining this W34, to get the enthalpy, you don't take the fraction into account. Same goes for this equation to get H8. What is H8? H8 is equal to H7 plus W78, whereby this W78 is equal to V P8 minus P7. So please take note that when we are going to determine the enthalpies of all states don't take care of the fraction, assuming that everything is as 1 kg of steam flowing. So that is how we determine all the enthalpies. Okay? If you look at the equation, there's one more parameter that we need in order to get the thermal efficiency, to get the SSC, which is the Y value. Okay, the Y value. If you want to get the Y value, then you need to look at the schematic diagram. If you are not well versed, you're not understanding how to get the Y value, then you look what I have mentioned last week, whereby we are going to see the energy balance equation looking at the feed water heater. Okay, feed water heater. So this is our feed water heater. Let me put it clear right here to see the equation or the energy balance to a feed water heater. Take note that we have looked how to solve all the enthalpy. Okay, all the enthalpy have been solved, but there's one parameter that have not been solved is the Y, the amount of bladed steam. Right? So let us look the energy balance of this feed water heater in order to determine the Y value. Okay, again, I'm repeating that. Bear in mind, we have solved all the enthalpies. Okay, as far as the time we have solved this, 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 and this. So we don't need the H5. So now the energy in at point 4, the fraction of flow is 1 minus y. 1 minus y, H4. And the flow in again is at 6, which is y, H6. And this is equal to the energy coming out from the heat water heater. So this is H7. Okay, the energy balance should be the energy in at 4 plus the energy in at 6 equal to the energy out at 7. So this is the part energy in from the pump, which is this one. This is energy from the bladed steam, and this is equal to the energy right here, whereby the fraction of 7 is 1. So remember that I mentioned that we have all the enthalpies. So from this equation, the purpose of this equation is to calculate how much steam is being bled off. Where is the Y? Okay? Any question, guys? Yeah, any question? No question. Okay. So if there is no question, let us look at one example. Right. So let me print screen of this. Yes. Okay, this is the schematic diagram of the example that we are going to look into. Okay, what do you think of this schematic diagram of this plant? What is the case? We have boiler right here, we have superheater in here, then we are going to get the steam going into the turbine, which we have the high pressure turbine. Then we are going to divide two flow. One is the flow to the feed water heater, which is an open type. And then the balance of the flow, which is 1 minus y, we are going to reheat it again, right, in the superheater side. And then we are going to expand to the second turbine, which is the low pressure turbine. Then coming out from the low pressure turbine, we are going to send into the condenser side. And then coming out from the condenser, SH5, we are going to flow or to increase the pressure from 5 to 6. And this 6 pressure is equal to pressure of 2. And then what is coming out, right, the mixing of these two flow from the condenser and the blade steam, and coming out at 7. And then we have the second compressor, the pump, feed water pump, and we increase the pressure to P8, which is equivalent to the pressure of this boiler and superheater, right? So this is the regen. Okay, this is the regenerative cycle with open feed water heater and reheat. Okay, and reheat. So this is the case. We have reheat process in between the two-stage expansion in the turbine. Okay, so that is our case. And I'm going to give you the properties for each condition right here. So this is the properties. Let me print screen first. Okay, these are the properties. The given properties. All right. This is the temperature involved for inlet. And this is the temperature involved for the inlet of the second turbine. Okay. And in this case, we are given the isentropic efficiency for the each turbine. Okay, for each turbine. And then the pressure of this boiler is as what we have before. This is 4000 kPa. And then we have P2 is 600 kPa. And then the P condenser is 40. So we have 3 pressure: high pressure, low pressure, intermediate pressure. And this intermediate pressure is the pressure of the feed water heater. Okay, so if you look right here, for an open type of feed water heater, which we allow a direct mixing of the blade steam and also the condensate from the condenser or after the pumping process, the pressure of P6, P2, and P7, they are equal. Okay, P2, P6, and P7 coming out, okay, the pressure should be the same. That is the condition for an open feed water heater. They must operate at one pressure. Okay, the feed water heater open type, they must operate at one pressure. Meaning that if one pressure, we are going to have P6 equal to P2 and equal to P7. Okay, so the pressure of one, okay, we are going to get the pressure of P1 is equal to 4,000. So we are going to use. And then the pressure of intermediate, which is equal to P3, this is equal to 600. It's the value that we are going to use. And the pressure of the condenser, which is a P4 equal to P5, we are going to use this as 40 kPa. Okay. So how to get the H1? To get the H1, we are going to base on P1 and T1. How to get the H2? The H2, we are going to get from the isentropic efficiency for the turbine of high pressure. And before that, we need, in order to get the H2, we need to get the H2S. And then this H2S is basically based on the P2 and also S2S, which is equal to S1. Then to get what is our H3 is basically based on the P3 and also on the T3. After that, we are going to get the H4S, as you know. In order to get what is H4, we need the H4S first. Okay, so what is H4S? H4S is basically based on the pressure of 4, P4, and also the entropy of 4S, which is equal to the entropy of 3. All right. So from here, we are using the isentropic efficiency for the turbine low pressure, the equation of this. Then from here, we will get H4. All right. And then how to get H5? H5 is equal to the HF at P5, condenser pressure. And how to get the H6? H6 is equal to H5 plus W, or I just put the formula right here, V P6 minus P5. Okay, so we have done the 6. Now how to get the H7? The H7 is equal to the HF at P7. How to get the H8? H8, this is our H8. Okay, what is H8? H8 is equal to the H7 plus V P8 minus P7. So this is how you get all the enthalpy. And lastly, how to get the Y value. So this is our schematic diagram of the open feed water heater. The energy in, right, equal to the energy out. So please take note that right here, the fraction of flow is 1 minus Y. Same goes for this part. This is 1 minus Y. So Y plus 1 minus Y, what we have at 7 is 1. Okay, so if we write the energy in equal to the energy out, or the energy balance of the open feed water heater, then we are going to get Y H2 plus 1 minus Y H6, which is equal to H7. So this is the equation or the energy balance purposely to get the Y value. Okay, so after getting all the enthalpy and also the Y value, then we can get the individual energy in terms of work and also in terms of the heat involved. Okay, work and also the heat involved. So let us look how to get the work and also the heat involved. Right. So W12. This is equal to H1 minus H2. W34, which is equal to, remember, at point 2, we bled Y. So the balance of W34 should be 1 minus Y. So we put here 1 minus Y, H3 minus H4. Okay. And then the work for pump, W56, this is equal to 1 minus Y, H6 minus H5. We have obtained the H6 right here. And then the W78 is equal to H8 minus H7. So this is, as far as the work is concerned, this is what we have. And then for the Q in, right, we have two stage or two type of Q in right here, which is the Q8 to 1, and also we have Q of the reheat, which is Q to 3, where the Q81 is equal to H1 minus H8. Then for the Q23, which is the Q for the reheat process, we know that at point 2, we have bled Y, so the balance for the reheat is 1 minus Y. So this is 1 minus Y multiplied by the H3 minus H2. H3 minus H2. So this is the work and also the analysis of the heat. And after this, we could get what is the W net. The W net is W12 plus W34 minus W56 minus W78. That is W net. And then after that, we get the thermal efficiency, which is W net divided by Q in. And then we get the SSC. The SSC is 3600 divided by W net. Okay, that is our interest parameter. Number one is the W net. Which is equal to the W turbine high pressure, which is 12, plus W for the turbine low pressure, which is 34, minus W for the first pump, 56, minus the W for the second pump, 78. We have obtained the Q in before this. Then this will lead us for the thermal efficiency percentage. Then second parameter, which is our interest. Okay, this is our second parameter of our interest. This should be the third one, which is equal to SSC. The formula, we have two formula, 3600 divided by W net, or this is 3600 M dot divided by W net. So this is also power. And this will lead us the unit of kilogram over kilowatt hour. The last one that we have learned is to get the work ratio. And what is the formula of work ratio? The formula of work ratio is equal to the W net divided by the W gross, where the W gross is equal to W12 plus W34. So this is all the formula of our concern, and usually is the one that we need. Okay? Any question, guys? Guys, any question? No question.
Sir, can you scroll up to number 1 and number 2?
Number 1
scroll up a bit. Zoom out also can.
Okay.
Okay, correct. Thank you, Doctor.
Right. Okay, okay. Are you okay? All right. So this is what we have discussed. So this is all the enthalpies involved at the particular pressure. So you are getting H1, H2, H3, H4, and H5. And this is, you have learned in thermodynamics. Of course, you need to know what is your state. Okay, the tricky part is to get the state of 2S2, 4S, and 4. You need to prove that in this case, what is the state of that? Okay, so please take care of this. You need to determine the state, state and state, because you could have 2S mixture, 2 mixture, you could have 2S mixture, 2 superheated vapor, or both in the superheated vapor region. Same goes for point or state 4 and state 4S. Again, I repeat, you could have 4S and 4S mixture. You could have 4S mixture for superheated vapor, or you could have both at superheated vapor. So you need to prove that. 5, 6, no problem. 5 is always at saturated liquid. 7 also as saturated liquid. 6 and 8, compressed liquid. Okay, compressed liquid. 1, of course, because this is 400 greater than the critical point, then it should be superheated vapor. And then you see the heat process, because the 2 is at superheated, then if we reheat, then it will go further up at the superheated vapor region. So of course 3 is superheated vapor. Now you see how to determine the H6. When you determine the H6, don't take the Y into account. In this case, it's 1 minus Y for H6. You just get what is the value of 5, 6. Okay, don't take into account the 1 minus Y. So this is how you get your H6. And then for the H7, H8 again, H8 is equal to H7. H8 equal to H7 plus W78. You see right here, we don't take care of the Y, or in this case it's 1. Right? So this is your W78, and then this is your H8. And then you see your energy balance equation for the steady flow energy equation. At the feed water heater, this is the energy balance. Okay, just rearrange back, then you get your Y value. So what is Y? The final equation for Y is H7 minus H6 divided by H2 minus H6. So this is your Y value, the fraction. You see, I don't put any kg right here. I just leave it as a fraction. Okay, as a fraction. This is how much the fraction of black steam for every 1 kg of the steam flowing in the plant. So if the plant flowing is, let's say, is m dot, then you multiply by m dot. Okay, so that is to get the Y value. And then this is how we get the W net. 1, 2 plus 3, 4 minus W5, 6 minus W7, 8. Okay, so this is your individual value. You see the fraction of flowing at W12, which is your high pressure turbine, is 1. And then at the 3, 4, the W or the flow fraction is 1 minus Y. So you must put 1 minus Y when you determine the W3, 4. And then next is to determine W56. You see, when you get your W56, in order to determine the work, then you put your 1 minus Y. Previously, we put that 5, 6, we don't take care of the 1 minus Y in order to get H6. Okay, so here we put 1 minus Y. And then this is our W net. This is our Q in. The Q in for boiler and superheater is 1, but for the reheat cycle is 1 minus Y. So this is 1 minus Y. So this is your Q in, the total of heat input at the boiler side, the boiler, superheater, and also the reheater. So this is what we get in terms of the thermal efficiency. And then the last one is our SSC. Okay, this is our SSC. Okay, guys? Any question?
No, doctor.
No, doctor. No question. Okay. So I'm going to forward this solution to our group. This is feed water open class exercise. Okay. Let me get that first. Where is our group? 2423. 2423. Okay, attachment. File. This one, 2423 material. Okay, this one. Steam cycle. List. What is the file? The file is feed water heater open class exercise. Okay, this one. Okay, guys. So we better try. Okay. I've given everything so that mistake I made, just let me know. Okay, let me know. Got it, guys?
Yes,
Got the
doctor.
file? Okay, thank you. Now, what are we going to do next is to look at one question. Feed water heater open. So, this is not the one. Question. Okay, what's this? Question. Where is the question? Plan class exercise. Okay. Let us look at the second question. All right. Green screen. Please. We are going to look at problem 1046 taken from the University textbook at the 7th edition. 7th edition. This is involving the open feed water heater. Sorry. Copy. Okay, this one. This is involving mass flow rate. Okay, mass flow rate. A steam power plant operates on ideal regenerative cycle with 2 open feed water heaters. Steam enters the turbine at 10 kPa, 10 megapascal, and 600 degrees C, exhaust and exhaust to the condenser at 5 kPa. Steam is extracted from the turbine at 0.6 and 0.2 megapascal. Water both what is that? Both water heater are saturated. Oh, okay. Both feed what both macam mana ni? How come this sentence water both feed water heater? Oh, okay. Water both feed water heater is saturated liquid, meaning that the state after the feed water heater is as saturated liquid. The mass flow rate of steam through the boiler is 22 kilogram per second. Show the TS diagram and determine the net power, right? Then we need the thermal efficiency, and then we need the specific steam consumption. Okay, specific steam consumption. Okay. In this question, we are looking at the usage of 2 feed water heater. Both is open type. Okay, both is open type. Right. So can we sketch the schematic diagram of this type of feed water heater? How many turbine is there? How many turbine? We have 2 feed water heater, which is open type. Then if we look right here, this is ideal regenerative cranking cycle. What is the meaning of ideal? The meaning of ideal right here, there is no isentropic efficiency. Okay, there is no isentropic efficiency. That is meant by the ideal, meaning that the expansion process in the turbine is isentropic. Okay, we don't take care of any, this question does not give us any isentropic efficiency. And then given right here, the pressure, the high pressure side, okay, 10 megapascal. And then the low pressure side is 5 kilopascal. And then the steam is extracted from the turbine at 0.6. Two extraction, because why 2 extraction or 2 bleeding? Because we have 2 feed water heater. Okay, 2 feed water heater. And then the mass flow rate is 22. Okay, the mass flow rate of the steam through the boiler is 22. Okay, now we need to sketch the arrangement of this. So we only have one turbine, meaning that we could not have any reheat process because only one turbine. So if we sketch the turbine right here, this is our turbine. And remember, we have 2 extraction. 2 extraction for the turbine. Okay, the first extraction, feed water heater. Let's say this is a feed water heater 1. And then the second extraction will go to the feed water heater number 2. Okay? So this is our output from the turbine. Let's say is running an electrical generator. So let's say this is our electrical generator. So what is coming out from the turbine? We are going to flow it to a condenser. So this is our condenser. Okay. And then right here, after the condenser, we must have a pump because the condenser right here is the lowest pressure, whereby the feed water heater number 2 is working at different pressure. Okay, and this feed water heater in the question is given the extraction pressure. Here, okay, the steam is extracted from the turbine at 0.6. So this should be at 0.6 megapascal. And the second extraction should be at the 0.2 megapascal. While the condenser pressure is given right here as the 10 megapascal. So right here is 10, sorry, 10, not 10, 5, sorry, 5. The condenser is 5 kilopascal. While the boiler pressure, which supply the steam to the turbine, is at 10 megapascal. So this is given as 10 megapascal. And remember, the pressure is given right here, the temperature given right here is 600 degrees C going into the turbine. Steam enter the turbine, 10 megapascal, 600. So 5 kilopascal is the condenser. So this is coming to the condenser. Extracted, first extraction, bleeding is 0.6. Second extraction is 0. Remember, I explained just now, the feed water heater will operate at one pressure. Okay, the same pressure. The steam extracted going into the feed water heater and the mixing will happen at the same pressure. Meaning what? Meaning what is entering the feed water heater is at 0.2. Remember right here, the 5 kilopascal is condenser pressure. Meaning what? Meaning we must have a pump right here. So this is feed water pump. Okay. And then coming out from this feed water pump number 2 is at 0.2 megapascal. Then we are going to mix it with the feed water heater right here. So this is 0.2, this is 0.6. Meaning that we need to increase the pressure as 0.6. So we need another pump right here. So this is feed water pump again. You want to increase from 0.2 to 0.6. Okay. And we know that the boiler right here is at 10 megapascal. Now, what is coming out from the feed water heater number 1 is 0.6. So we need to increase to 10 megapascal, meaning that we are going to have another feed water pump right here to increase from 0.6 to 10 megapascal. Then only it will go into the boiler. This is our boiler side. Okay, this is the drum. This is the superheated accumulator. Then it will go to the superheater. What is coming out right here is superheated vapor. So this is the boiler. This is the drum receiving the saturated vapor, right? So it's coming out right here. So this should what our schematic diagram should look like. Turbine, first extraction, second extraction, the supply from the boiler, superheated vapor, and then coming out. While expansion, we have 2 extraction, and then going to the condenser at 5 megapascal. We are going to increase from 5 megapascal to 0.2 megapascal at the feed water pump, number 1. And then at the second feed water pump, number 2, we are going to increase the pressure of 0.2 to 0.6. And then we are going to increase again the pressure using the feed water pump number 3. We are going to increase 0.6 to the pressure right here, which is equivalent to the boiler pressure, which is 10 megapascal. And we increase the temperature to 600 before entering the turbine. So this is our schematic diagram look like. Okay? So, how are you going to number it? Giving the numbering. Which numbering that you want? Which is number 1? Which state you want to give as number 1? Come on. Give suggestion.
At the entrance of the turbine.
Entering the turbine. Okay. So this is the arrow. This should be the arrow. This should be the arrow. Is there any missing arrow? Oh, yeah, this one. So you see, for a feed water heater, it must work in between feed water pump. Okay. So if we have 2 unit of feed water heater, we need 3 unit of feed water pump. See, because feed water pump must operate in between feed water heater must operate in between feed water pump. So here, feed water heater number 2. Here, feed water heater number 1. Okay. So the first extraction, let us give this the name of the first extraction is Y. This is how much blade steam is going to the feed water heater number 1. How about this one? What numbering that you want to use for the Y? Let's say this is Y. You want to name this is Y because we have 2 Y right here. Okay, this is, let's say this is Y1. This is Y2. Okay, Y1, Y2. So you want to number this as 1. Right, this is 1. This is 2. So this should be 3. This should be 4. This should be 5. This should be 6. Oh, 6. This should be 7. This should be 8. This should be 9. And this should be 10. So we have 10 states. Okay, 10 states. So this is ideal, okay? This is ideal regenerative Rankin cycle, meaning of ideal, we don't have any isentropic efficiency. Okay, we don't have any isentropic efficiency. All right. So this is the schematic diagram. Then we are going to sketch the TS diagram. TS. All right. But bear in mind, the state of expansion, the state of 2, the state of 3, and the state of 4, we are not sure whether it's going to be superheated or mixture, right? But we need to get a guide. We need to sketch the expansion process. For sure, we have four pressure. Highest pressure, which is the boiler pressure. This is your first bleeding process for the feed water heater number 1. This is the second pressure, which is the extracted steam or bleeding steam at feed water heater number 2. And this is our condenser pressure. Right? So if I project the pressure, okay. For sure, state 1 is superheated. Why is superheated? Because right here is 600 degrees C going into the turbine. So if 600, then we are getting a superheated vapor, 600 degrees C, because we know that the T critical is at 373. So 600 is greater than T critical, it should be superheated. And then if we try to sketch the process of expansion in the turbine, if I use this point as my guide, then I'm going to have this type of expansion. And this is 1, this is 2, this is 3, and this is 4. You see, at the expansion part, 1, first to 2, and then 2 to 3, and then 3 to 4. Okay? But please take note, 2, 3, and 4, we need to determine the actual state. What I have right now, based on my sketching, as though that I'm getting the 2 is superheated vapor, 3 is superheated vapor, and 4 is mixture. I could be wrong. Okay? I could be wrong. Then you need to prove the state. Okay? You need to prove the state. Then to complete this diagram, I need to project all the pressure to the left, condenser, feed water heater number 2, feed water heater number 1. This is the boiler pressure. Again, I'm going to project at the compressed liquid region for the pressure. Okay. And then we have 3 pumping process. Okay, 3 pumping process. Vertical, this is your isentropic. This is should be the first 5 to 6. This is 5. And this is 6. And then we had the increase of temperature due to a feed water heater. which we have here 7. And the increment 6 to 7, because of the extraction of feed water heater number 1. Number 2. Okay. And then we have the pumping work 7 to 8. So this is 8. And the increment from 8 to 9, this is 9, is due to the heating process in the feed water heater number 1. So we are getting the amount right here. And then we have the next compression or our pumping process, the feed water pump number 3, 9 to 10. System. And after that, from 10 to 1 is the heating process in our boiler and superheater. Then complete the 4 to 5 condenser. Right? So let's say this is 1. The fraction of flowing at the boiler is 1. Okay. The fraction of bladed steam for the first feed water heater is Y1. For the second feed water heater is Y2. And the balance is going to the condenser, which is 1 minus Y1 minus Y2. Okay? We complete the TS diagram by putting all the arrow of the process. Okay guys, any question? So this is our TS diagram. The first part is schematic diagram. Now this is the TS diagram. Any question? Any question?
No, doctor.
Okay. So let us remind that this is 10 kPa, right? This is, 10 megapascal boiler. And then we have right here is 0.6 megapascal first feed water heater. This is 0.2 megapascal for the second feed water heater. And this is 5 kPa. Okay. Now, let us look at point 2, 3, and 4. Okay, point 2, 3, and 4. I want to determine actually what is the state. So, of course, to get the state 1 is superheated vapor. That is H1. H1 based on P1 and T1. Okay. And then H2 is basically on P2 and S2, which is equal to S1. Could someone get what is the S1? The S1 is 10 megapascal, 600. Can someone get for me? How much is that? entropy releases water. 10 megapascal. From here also we are going to get, we need to determine from here is the S1. Guys, anyone? Don't let me do it alone, please.
6.9045.
Let me check. Okay, others? Any comment on that value?
Same answer.
Same answer, sir.
Same answer or same
Got the same value.
Same value. Okay. We haven't got any answer, right? We haven't trying to answering anything. So based on 10 megapascal, S is 6.9045, correct?
Yep, correct, doctor.
Okay, good.
Kilojoules per kilogram K Kelvin.
All right. So this should be our value. Undo. Okay. So this is in kilojoule over kilogram Kelvin. Okay, now determine the state of 2. 0.6 megapascal. Hmm. 0.6 megapascal. 0.6 megapascal. How much is the SG? 0.6 SG, 6.75, correct? Hmm. 0.6 megapascal. The value of SG is 6.75, correct? Anyone?
Yes, doctor.
Yes, sir.
Yeah, so what we have,
7593, right, doctor?
pardon?
6.7593, right?
Okay, you take note of that.
Okay.
But what I could get from here is the S2 is greater than SG at 0.6, correct? Therefore,
Superheated, sir.
superheated vapor. So we have this correct, we have this correct. Now H3 is based on P3 and also S3 equal to S2 equal to S1. So what do we have? Which is equal to 6.9045. But now we have to refer to 0.2. 0.2 megapascal. SG is 7.1270, correct?
Correct, sir.
So what we have?
Yes.
We have right here
Calculated,
the S3 is greater than SG at 0.2, correct? Okay? Therefore, okay, kalau kita lihat jadual 0.2 SG is 71270. Here is 6.7045. Oh, I'm not doing it right. Less kan?
Yes, doctor.
SG is greater, sir.
Huh?
SG is greater.
Okay lah, maknanya S3 is less than,
Is less than SG.
therefore,
Therefore, it's saturated mixture.
So it's mixture. So what happened? We got this wrong, correct? Correct. S3 is wrong, right? And then state 4. We are using to get the H4 based on P4 and also S4, which is equal to S3 equal to S2 equal to S1. Right? The same value, 6.9045. But right now we are going to get at 5 kPa. 5 kPa or 50 kPa? 5 kPa, right? The question is 5 kPa, yeah, 5 kPa. So kalau 5 kPa, the SG, 5 kPa, SG is 8.3938. So what we are getting right here, the S4 is less than SG at pressure of P4. Therefore, again, we are going to have mixture. This is correct. This is wrong. So we need to adjust. Okay, we need to adjust this point. So can you please adjust it for me? Okay, you have to put it the process 1 to superheated vapor, 2 to 3 from superheated vapor to mixture, and then 3 to 4 is a mixture. So you are going to have this type of expansion process. Okay, so you need to get it. This is 1, this is 2, this is 3, and this is 4. Okay, so that is our. So in order to get the H3 as mixture, then you need to use what? H3 is equal to HF3 plus X3 HFG3, whereby the X3 is equal to S3 minus SF3 SF3 divided by SFG3. Then from here you will get your H3. Same goes for the H4, because it's superheated vapor, this mixture, sorry. So H4 is equal to HH4 plus X4 X4, and this is a HFG4. Then you need to get your HX4. X4 is equal to S4 minus SF4 divided by SFG4. And once you get your X4, then you will get your H4. Okay. Then again, you get your H4, H3. Okay, based on the H2 is based on P2, S2. Then you get your H5. What is H5? H5 is HF at 5 kPa. What is H7? H7 is equal to HF at 0.2 megapascal. What is H9? H9 is equal to HF at 0.6. How to get the H6? H6 is equal to H5 plus work 5/6, or H6 is equal to, anybody? The equation? H6 is equal to H5 plus V P6 minus P5. What is H8? H8 is equal to H7 plus V P8 minus P7. What is H10? H10 is equal to V P10 minus P9. Okay? So what is H5? H5 is equal to HF at 5 kPa. What is H7? Or before that, H6. H6 equal to H5 plus VP6. P6 minus P7. Sorry, yeah, P6 minus P7. No. Sorry. Wrong kan?
Nak cari H6 kan, Doktor?
H6, saya salah ni. Sorry. Okay. H6 is equal to H5 plus VP6 minus P5. Then H7. H7 is equal to HF at 0.2 megapascal. H8 is equal to H7 plus VP8 minus P7. H9 equal to HF at P9 is 0.6 megapascal. Okay. After 9, H10. H10 equal to H9 plus VP10 minus P9. So that is all the enthalpy. Okay, that's how we get all the enthalpy. Okay, so after that, we are going to get what? The W. Okay, the W for each case. Oh, sorry, not the W. What do you think that the next thing that we could get? So this is how you get your all the enthalpy. Erase that. After the H10, what do you think that we are going to get? Guys?
Value of y?
Yes. The value of y. Okay. Which y do you think that we get first? The y1 or y2?
Y1.
y1. Okay, if you set y1, then we try to get y1. Let's see together whether you get it right or wrong. So if y1, we are going to look at this part, correct? So for y1, we are going to look at the feed water heater number 1. So we are going to look at the feed water heater number 1, the energy balance. Y1 H2 plus what is flowing at 8? What is flowing at 8?
Y2.
This is Y2. This flowing, okay, this flow is 1 minus Y1 minus Y2. Ingat This is Y, correct? This is Y2. So the balance right here is 1 minus Y1 minus Y2. So the 1 minus Y1 minus Y2 is going to flow at this path. Then entering at 6, Y1, okay, 1 minus Y1 minus Y2 plus Y2. So what we have here is 1 minus Y1. Correct? Come on. Correct? I repeat it again. What is flowing right here is 1 minus Y1 minus Y2. So this is flowing to here and then going to mix with Y2, correct? So if Y2 plus 1 minus Y1 minus Y2, so what are we going to have right here is 1 minus Y1. Okay? So this is 1 minus Y1 H8. And this is equal to 1 Y1 plus 1 minus Y1. What is coming out at 9 is 1. So this is equal to H9. Okay. So from here, we solve the Y1. Because we have all the enthalpy except for Y1. So we can solve for Y1. And then we look at the feed water heater number 2. So this is our feed water heater number 2. What do we have? Number 2, this is, feed water heater number 2. What is flowing at 6 is 1 minus Y1 minus Y2 H6 plus 3 plus Y2 H3. And this should be equal to what is coming out right here. Okay, this is 1 minus 1 minus Y1 H7. Okay, so what is coming right here is 1 minus Y1 Y2 times H6. What is flowing in here is Y2 H3, what is coming out right here is 1 plus 1 minus Y1 Y2, which left us 1 minus Y1 H7. So from here again, we have all the enthalpy, and also we have the Y1 from here. So this should solve our Y2. Okay, so this equation, by looking at the feed water heater number 2, we are solving for Y2. Okay guys, trying to get all the enthalpy, okay, and we are going to continue tomorrow, inshallah. Okay, try to get all the enthalpies, or you can, if you can go ahead, solve for the net power output, and then solve for the thermal efficiency, and solve for the specific steam consumption. Okay, so I'm going to get your attendance right now. Any question, guys? Okay, so this is your attendance. Right. So tomorrow we are going to continue this question, and also we are going to look into the feed water heat